All right, so we're going to start a few lectures on rotational dynamics. We've talked about that when we were doing 2D kinematics, but kinematics just deals with like where and when a particle is. Rotational dynamics is more of dealing with an entire like chunk of something that's actually rotating versus just some point particle traveling in a circle. So we're going to start thinking about Newton's second law, F equals ma, except we're going to map it to a rotational setting. And that's where torque comes in. So for those of you that may already be familiar with torque, you can think about it as like a force applied to an object that's going to make it rotate. So normally we talk about forces that are actually pushing an object in some linear direction back and forth. But this time we're actually talking about forces that specifically cause some sort of rotation. Okay, so with rotational motion, the particle model that we've been using, especially in the 1D and 2D kinematics at the beginning of the semester, the particle model doesn't incorporate the characteristics of the object itself. So if you think about it, the particle model is just the one point, but if we had some sort of maybe circular object that's actually undergoing some sort of rotation, that's never actually, we can't model that with a single particle. So the idea here is we need to sort of zoom in on these objects instead of treating them like particles and actually look at how the dynamics of the object itself is going to change its dynamics. So for extended objects, the size and the shape, they do matter. Especially like, if you have an object that's maybe heavy on one end and lighter on the other, and you want to rotate that, that's going to be very different than just rotating like a mass that has like uniform mass density. So for a definition, a rigid body is just an extended object whose size and shape do not change during movement. So it's not like we're throwing a spring or a slinky and it's going everywhere while it's rotating. We're focusing just on the characteristics and dynamics of something that's not very flexible. So there are three basic types of rigid body motion. We have one we've been talking about, the translational motion, where we just have an object moving in one or two directions. We know how to deal with that. That's just 2D kinematics. We also have purely rotational motion, where something is not moving in the XYZ domains, but it is sitting there spinning around one specific point. So you can see here, this object is rotating about this central point, but that central point itself is not moving anywhere. It's not translating across the page. And then, of course, we could have a combination. So in that case, you can see we have this baton, I guess, being tossed. Not only is its center moving, as you can see, but it also is undergoing some sort of rotation in the air while it's being thrown. Anytime one of these objects is spun without any translational motion, it will naturally rotate about the center of mass. So the center of mass is essentially the little red dot I put on that previous slide. That's the one point that's not actually moving in some sort of circle. It's completely stationary, and you could imagine if I were just sitting in my office chair spinning, that would kind of be like the center of mass. It itself is rotating, but it has no length, it has no distance like a arm of rotation. It's just sitting right in the middle of the object. So that's the center of mass. So yeah, again, it remains motionless while every other point on the object undergoes circular motion around it. So here's where we have that like center of mass. Every other part of an object will have some radius away from the center of mass it'll be rotating around. Now, a good question would be, how is the location of the center of mass calculated? Because if we want to do these rotation problems, or if we're thinking about something thrown or put into rotational in the International Space Station, we want to know about like what point it's going to spin, because on the ISS there's no gravity, so anything will naturally want to spin around its center of mass if it's in space. So to figure out where this point is, what we need to do is we need to treat the object like a collection of small particles where each one has a mass m sub I. Okay, so we're going to take whatever object it is. I don't know, maybe we could take like a weird loaf of bread looking thing. So what we'll do is we'll just divide it up and say, okay, well, here's all these little pieces of the object. They all have some sort of mass m sub I. Okay, and they all have positions. Like even this position, this point here, if we were to slap a coordinate system on this, this mass m sub I would also have a position at xi and yi. So every single one of these points on this object will have some sort of tiny mass associated with it, and it'll have an xy position. Okay, so here's our random mass that we want to calculate the center of mass of. So what we want to do is we want to calculate a weighted average of all these little particles, all these little pieces of the mass. And essentially a weighted average is much like a regular average, but we're just going to assign a weight to each thing. So you can imagine if I wanted to find the average x coordinate, so if I wanted to find the average x coordinate, I could just sum up all of these x coordinates already here, and then divide by the total number of them, and that would give me where the average x position is. So I'd say the average x position might be right here. I could do the same thing if I wanted to. Sorry, there we go. I could do the same thing if I wanted to and actually calculate the average y position. The thing is, we treat all these coordinates the same. They're all equally weighted. Just kind of like if you want to find the average of your test grades, you don't make one test way more than another test. They're all the same thing. They're all tests. So if you have 3 tests, you average as 3, done. Now with a weighted average, which is what we're doing here, what's going on is we're actually going to weight each individual coordinate. So if you look at my formula here, especially right here, we have this m times x. So the idea is, just like with our average coordinates down here, what we're actually going to do is take each x and then weight it by its associated mass. So we still have each x here. And we go from, the first one, x sub 1, all the way up to x sub n. But then for each one, we're actually going to weight it by its associated mass. Okay, now we also have to cancel out those weird units. So we have an m, a mass, so kilograms, times a distance, so that'd be meters. So up here we have these kilogram meters. Okay, well that's weird. We don't want kilograms. So what we do is we divide by big M, or the total mass. So it's all these things added up divided by the mass of the whole thing. And I mean like the mass of this whole thing, our whole object. Big M is what we're after. Okay, now see this denominator right here, this M1 all the way up to M sub n. That's taken care of out here. So that's the 1 over n, big N, where big M is the total mass. Okay, and I've mentioned that right here. Big M is just all those, the masses summed up. We don't care where they are for big M. We just want to know what the sum of all those masses are. And then, of course, we can do the same thing for the y center of mass, or the y coordinate center of mass. Just mass weighted, divide by the total mass, And what actually comes out of that is one value for where the center of mass, the x coordinate for the center of mass is, and one value for the where the y coordinate of the center of mass is. And we'll do some examples shortly. So essentially, when we want to say where the center of mass is, we can just do this simple calculation. Now you'll notice that particles of larger mass, so if there's a piece of this object that really weighs a lot versus some of the other ones that are kind of light, you'll notice that these larger masses count more than the particles of smaller masses. And that's where these terms come in, the n's. So put a big number in there, that particular x value or y value will count way more for the location than if it's just a little tiny piece with not a lot of mass. For a continuous object, so instead of maybe we have such fine chopped up pieces of our object, maybe we want to actually turn this into an integral instead of just trying to add up, millions of little tiny pieces. So for this continuous object, we can actually take our summation and turn it into this situation here where it's essentially infinitesimally small masses. So our delta mi here, so here's a really small chunk of mass. We essentially dump that into our original equation and then make them really, really small. So as the limit approaches 0, we keep chopping this up even more. Turns out we actually can turn this into an integral. So here we just need to integrate across all the x coordinate, and with the y component, the center of mass, we just have to integrate across all the y's. So the whole idea, just like on the previous slide, if we have some weird object like this, okay, we can actually keep making all of these little mass chunks smaller and smaller and smaller, and then finally we can integrate over it. So this is the formal definition of the center of mass, but the dm here, this little mass infinitesimal, we normally don't integrate across masses. We actually integrate across like a dx, dy, or dz. So the catch here is that anytime when you have this dm, what you need to do is you have to change the dm. So the dm must be changed. Integrals are carried out over coordinates. So we have to find a way to relate a dm to a dx or a dy or a dz. So let's look at an example here. This one, we don't even need to do an integral yet. We're just going to take it slow and look at something more simple. So we have this 500-gram ball and a 2-kilogram ball connected by a massless 50-centimeter long rod. Okay, as always, I've drawn everything. So I've got my 2-kilogram mass here. I've got my 500-gram mass here. I've got their distance. Distance is laid out from 0 to 0.5 meters, 50 centimeters. Now I've got my center of mass labeled here, but I need to change colors, something that shows up better. I've got my center of mass labeled here, but I don't know what the value is. Right? We need to figure out exactly where that is. Intuition will tell you that it will probably be closer to the bigger mass. So we're going to assume that it's probably going to be closer to the bigger mass because, remember, larger masses affect the position of the center of mass more, okay, because it's a mass-weighted average. Okay, so we want to figure out where the center of mass is, and we want to know what the speed of each ball is. If this thing is actually rotating, maybe it's coming like out of the page, maybe it's rotating this way, I don't know. But if this thing is rotating about the center of mass at 40 RPMs, I want to know what the tangential velocity is of each ball. So if the center of mass isn't in the middle, each one will have a different tangential velocity. You'll recall that the tangential velocity, even though they're both spinning with the same angular velocity, the same omega, now they'll each have a different radius, right? So that means they'll each have their own separate tangential velocities because they have a different radius. Okay, so let's think about how we can calculate this. Okay, so here's my setup. Since this is all just in the x direction, and it's essentially just like a bar with some masses on the end, we only have to think about calculating the x component of the center of mass. Now, if we had one of these objects that was like setting way up high or down low, then we need to do both. But because they're all on the same plane here, we can just calculate the x coordinate for the center of mass. So I'll use my formula. Okay, so we have the mass weighted average 1 over total mass, and then times the sum. So here I just have my mass and position of the first ball plus my mass position of the second ball, and that's going to be divided by big M. Now all I have to do is plug things in. You'll notice that x1 is actually at the origin, so that's going to knock this term off. Whoops, that's going to knock this term off completely. It's 0. And then when we finish cranking this out, it turns out our position is actually at 0.1 meters. So I can update this. We know that this is 0.1 meters. And you'll notice that the center of mass is closer to the heavier ball. That's because the heavier ball accounts for more of this calculation. It's mass weighted, there's more mass there, that's why. Now for part B, we need to convert that rotations per minute to radians per second, so we can actually use it in our equations. Okay, so that's 40 RPM, which would be revolutions per minute. Now I just need to do my appropriate unit conversions to get this to radians per second. So it looks like there's 1 minute and 60 seconds, so that's going to get rid of our minutes, leaving us with seconds. That's what we wanted. Now we need to get rid of the revolutions. We want radians on top, so that's 2 pi radians per 1 revolution. Well, I've got a revolution in the numerator and the denominator, so I'm left with radians per second, which is exactly what we wanted. Okay, now we just multiply these fractions across, and we get about oops, there should be equals. We get 4.19 radians per second. Okay, now all I need to do is just plug that into our original equation to find these tangential velocities. So again, just a reminder, these things, the angle that they're sweeping out over time, that's the same. They have the same rotational or the same angular velocity. It's the different radius on each one. That's what's causing a different tangential velocity. So I can plug in those values. Looks like we have a radius of 0.1 because this is distance from the center of mass, right? Because we're rotating here, which means we have a distance here and a distance here. Okay, so this is distance from center of mass. Okay, we plug in these values and it looks like the first object, it's got a smaller tangential velocity. So it's just 0.42 meters per second. And then the second object, which is farther away from the center of mass, the second ball, has a tangential velocity of 1.68 meters per second. All right, let's look at another example here where we're going to calculate the center of mass. I believe we're calculating center of mass. Yes. So the last one, we just had 2 objects. That was a discrete example where we can see the individual objects. But with this example, let's actually talk about what happens when we have a nice continuous object. So let's consider a thin uniform rod of length L that loses mass such that its linear mass density is lambda naught on one end and lambda naught over 2 on the other. Okay, now we want to determine the location of its center of mass. So what that means is essentially there's some sort of mass, it's got some sort of density to it on one side here. Okay, we don't know what the value is, we just know it's lambda naught. And then by the time we get to the other side, it keeps getting it keeps getting less and less dense. So maybe it starts on one side as like some object of granite, And then by the time it gets to the other side, it's more like an object of styrofoam. So it just literally gets more and more, what's the word I'm looking for? Maybe squishy. Essentially, there's less of it, but it's taking up the same amount of volume by the time it gets over here. So that's just, it's got half the density that it started with. So essentially, one side might float while the other side starts sinking in water because the density through it is not the same. So we need some sort of equation that would represent this. And if you tinker with the math a little bit, you could actually come up with this. So this is my mass density. It's a linear mass density. That's why we're using lambda. So you'll notice if I plug in 0 for x, the second term goes away and we're left with lambda naught, which is exactly what we want at x equals 0. And then if I plug in L, the full length of the rod, well, I get lambda naught over 2. Perfect. That's exactly what, that's the equation we need. So this is the correct linear mass density. And the way to think about a linear mass density is essentially just tells us how the density or the mass of the rod changes across its length. So it's kind of like saying, well, the change in mass, delta m, for some chunk that you move across, delta x, is this, right? So in our case, it is this equation here. That's how our mass changes as we move across the object. Now, obviously, we can take those changes, those deltas, and make them really small and actually get a derivative, dm dx. So that's our linear mass density is just the derivative of the mass as we move across the object. And it's got units of kilograms per meters. Well, first, when we calculate the center of mass, we know we're going to need the total mass of the object because that's part of the process. You'll remember that the equation is y center of mass equals 1 over m sum yes, I literally almost just forgot what I was writing. Okay, so remember that it's this adding up all these pieces, but we have this total mass. Furthermore, since we're dealing with this continuous object, we still have that 1 over m out front, but we also need to actually wind up integrating this. Okay, so we're going to take our equation. Now, notice we're just calculating the total mass, okay? So we don't have the 1 over m out front. We need the big M so we can write the 1 over m later. Okay, so this eventually is going to go into the 1 over m. We just need the m value first. So we're going to add up all these little pieces, okay? It's a continuous object. So eventually we're going to, yeah, it's a continuous object. So we're going to make these delta m's smaller, right? So instead of a delta m, we're going to try and convert it to a dm. But here's the thing. The mass changes as we move. So what I want to do is I want to rewrite my delta m. Okay? My delta mi, I can rewrite it based off my equation for linear mass density. So what I'm going to do is solve for delta m. Now I know that's going to be times delta x. All I've done is I just took my equation up here and I multiplied my delta x over to the other side, okay? So now I have a delta m equals linear mass density times delta x. So I just substitute that in for my delta n. Now I can take this delta x and make it incredibly small. And when I make my delta x really small, it turns into an integral. So what's happening is I'm just going to integrate across the length of the object, 0 to L, across my mass density, because it's changing, okay? And that's just going to be in my x direction. So I can do that fairly easy. So I have my mass equals the integral over my linear mass density. Okay, well, now I can plug in my linear mass density, and that linear mass density has a constant out front. So I'll pull my constant out front. And again, just a reminder, I'm using this equation here. Okay, so I pulled that out front. Now I have this sort of gross integral in here. So I've highlighted it, and what I'm going to do is just a simple u substitution. So I take all of this, and I just say, well, that's equal to u, and then I can do a u substitution, calculate my du dx, and then just solve for dx, get dx by itself. Okay, so there's my dx, which means, and I will change colors here, which means I can replace this dx. This is the same thing as what I did with the dm dx, just changing out my differential at the end. What I'm talking about is right here. Changing out the dm with the dx. I'm doing the same thing. It's kind of like a u sum. All right, so now I've replaced my dx, and I have this much more manageable integral. Okay, well, remember I need to change my limits of integration. I trust that you guys remember how to do that. And then I just turn the crank, right? The integral of u is 1/2 u squared. And then I plug in my limits of integration. And it turns out the mass, total mass, is 3/4 L lambda naught. Now remember, lambda naught has units of kilogram per meter. So this L is going to cancel out that meter. So the units do work out. I'm left with kilograms. Still don't know what the actual mass of this thing is because I don't know what the L value is, the total length, nor do I know what lambda naught is, but it doesn't matter. I just know that whatever the mass is, it's 3/4 L lambda naught. Okay, I have the total mass of this thing now, even though it's just symbolic. Now that I have the total mass, we can turn the crank again and calculate the center of mass. Okay, so I'm gonna, once again, change my dm to lambda dx. So my dm is gonna become lambda dx. Again, that's just sort of like a u substitution. We're just doing it between mass and position. Okay, so I've plugged that in here because my lambda is those terms. I pull out the constant. You'll notice I went ahead and multiplied this extra x from the equation in there. And then all you have to do is just turn the crank. So I distributed the integral, and then so I distribute the integral, and I have two separate integrals. So from here to here, no new math has happened. I just rewrote it again to start the new line. So I integrate both terms separately. The lower limits on this integral are both 0, so that makes things a little easier. So I just have to plug in L twice and simplify. Now I still have this total mass floating around. So I still have this M here. And all I need to do is just plug in my M that I found earlier. Right, so I'll plug that in here, and then everything simplifies. So I've got 4/9 L. So you'll notice that the center of mass is it's almost right in the middle of this rod, because like 4.5/9 would be 1/2 L. So it's actually weighted a little bit more toward. So if this is actually L/2, okay, so this is L, this is 0. So it's actually over here just a little bit. My center of mass is. That's because this object is more dense on the left side than the right side. So it is going to be weighted a little bit more toward the more massive side. So for any symmetrical object of uniform density, the center of mass is always at the physical center of the object. So if this rod would have been uniform, as in the density would have been the same all the way across it, we could just pick the middle, and that's where our center of mass is. But because it was nonlinear, we had to do some calculus to actually find where it is, where the center of mass is. So that was a little more complicated problem. Everything, or most of the things you'll deal with in this course, they'll all be linear objects or with uniform density. But just be aware that when you get into like, engineering or harder sciences or harder engineering courses, you may have to deal with things that don't have a linear mass density, or they may be non-uniform. So then you'll at least need to be aware that this is the process you would have to go through to find these center of mass coordinates. All right, so the kinetic energy due to rotation is called rotational kinetic energy. Okay, so we're going to jump to, instead of just the dynamics, we're going to talk about the energy of these things. So how might we calculate this rotational kinetic energy? So essentially the idea is, if we just consider a uniform object rotating about an axle, or a non-uniform object, okay, so we have that here, right? This is our non-uniform object. It looks really weird, and it's going to rotate about this axle. Okay, well, we can think about this object as made up as a bunch of pieces, like individual pieces, just like we did for center of mass. So although it's a continuous object, let's just think about it first, 3 pieces, like here in this image. Okay, so if we think about the first 3 pieces, we know that the rotational kinetic energy is just the sum of all the kinetic energies making up this thing, right? So it's just the sum of the kinetic energies. Well, kinetic energy is 1/2 mv squared. So we just take the mass and the velocity of each of these pieces, add them up, and that's our rotational kinetic energy. Obviously, we need to keep adding them up across the whole object and not just 3 pieces. But this is just to show how the math looks. So obviously, each piece here has a tangential velocity. All right, you can see them here. So there's 3 tangential velocities. Well, really a bunch of tangential velocities, but we're just looking at 3. Now we need to relate this tangential velocity back to something about rotation. So maybe an angular velocity, because all 3 of these pieces have the same angular velocity, right? Same omega, different tangential velocity. So what we'll do is we'll change these velocities to r omega. Okay, so we'll take that, we'll plug it in. So really what you're looking at is this v squared in the 1/2 mv squared. We're going to plug in r omega. And you'll notice that omega doesn't have an index anymore. There's no I value. There's no 1, 2, 3, because it's the same for all of them. Okay, the only things that are unique to these pieces are their masses and their distance from the axle here, the point of rotation. So they still have separate numbers. So what I can do is actually just pull out the 1/2, because they all, let me grab a different color, they all have a 1/2. And of course, they all have the same omega. So what I can do is essentially pull that out, and then I'm left with this weird sum. So I've got the sum of mr squared, so the mass, which weights the radius squared. And this new term in here, which each piece is unique to each part of the object, because it's same 1/2 for everything, same omega for everything. All these little pieces of the summation are actually different and unique. So this actual term here, this sigma m(i)r(i) squared, is actually the object's moment of inertia. And it has weird units. It has units of kilograms meters squared. And essentially what it tells us, it's an object's moment of inertia. It depends on the location of the axis of rotation. So there is that r dependence. And what it tells us is essentially how much it's going to take to get that one particular piece moving. It's inertia, just like with Newton's second law. F equals ma. If there's a large mass, big M, it's hard to get that object moving. So if there's a large moment of inertia, it's hard to get that thing moving. Okay, and here again, the moment of inertia is the rotational equivalent of mass. Objects with large values of I are more resistant to rotation. So this is just like objects with large mass. they're hard to accelerate. It's harder to accelerate a car by pushing it than it is to accelerate like a bicycle. So an object's moment of inertia depends not only on the object's mass, so there is a mass dependence, but also on how the mass is distributed around the axis of rotation. So you can imagine there's ways to set up a bunch of masses to make it hard to turn them. There's also a way to set it up to make it really easy to turn them. So not only how much is there, but how it's distributed is very important when you think about rotational energy. So if we use the simple substitution and say, well, I is the moment of inertia, what we can do is rewrite the rotational kinetic energy, place this with just I, okay? And then there is our rotational kinetic energy, 1/2 I omega squared. Okay, that's purely rotation, right? This object could be moving while it's rotating, and that's a whole different kettle of fish. Right now, we're just talking about the energy from rotation. So moments of inertia for a lot of objects can actually be just looked up in tables. But if you have a really weird object that you're looking at, you might actually have to manually calculate I. So if the object is an uncommon one, you can maybe approximate it with an already known I value, but if you have something funky, you'll have to calculate it. So let's actually talk about what that process looks like. So we can guess where the center of mass is for a symmetrical object. Like, oh, it's a symmetrical object with a uniform mass distribution. The center of mass is going to be in the middle. We can't guess I. I is a little more complicated, so we'll have to do some calculations. So again, if we take a solid object and break it up into a lot of small pieces, then the equation actually becomes an integral, right? So we're just taking the r squared and then the m associated with each r squared, and we're making the masses really, really small, right? So our little mass chunks get incredibly small, which that's what turns it into an integral. So here r is the distance from the axis of rotation, and dm must be rewritten like we done in a couple previous examples. Dm must be rewritten in terms of a coordinate differential, so a dx or a dy. If an object is complex, we can actually divide it into multiple pieces with separate moments of inertia, so I1, I2, I3, and luckily for us, if we know the separate moments of inertia of an object, we can actually just add those up to get the total moment of inertia for some really strange object. So adding those up separately can actually be quite helpful. So what if we have an object that's rotating, like you can imagine this object here. Suppose we want to know what the moment of inertia for a rotation about an off-center axis is, and that's exactly what's going on in this picture. See, if we have this axis here that goes through the center of mass, that'd be an easy way to calculate the moment of inertia. Any sort of calculation about an object's center of mass makes it easy. But here in this picture, what you'll see is we actually have an off-axis axial here. So this thing, it looks like kind of like a bar of soap. It's just going to spin down and dangle maybe if we let it go. So it's not going to be like a nice circular rotation around the center of mass. It's going to have like this lobby side that's going to be spinning around. So now the question is, how can we calculate this moment of inertia easily for this really screwed up object? Because now it's got this really weird like clump hanging down and it's not nice and centered. So what we can use essentially is the parallel axis theorem. And what the parallel axis theorem says is that if the axis of rotation is parallel but offset. Now, do we have that? Yes, the green axis that I drew here is parallel to the axis through the center of mass, but it is offset, right? We can see that here. There's certainly an offset. So that meets our requirements for the parallel axis theorem. So if these conditions are met, then the new moment of inertia is simply the well-known moment of inertia if the axis is through the center of mass plus the offset. So the total mass of the object, big M, times the distance to the new axis squared. Okay, so again, that's my distance. Okay, so again, I, center of mass, is the known moment of inertia if the rotation is through the center of mass. So that's a big thing, if the rotation is through the center of mass. And then m is the mass of the object, and then d is the distance to the actual real axis of rotation. So that's just a cool trick. If you want to know where that comes from, you can look in the textbook. We won't cover that here, but you can look at how that's calculated. So here are several actual known moments of inertia, depending on what you want to do. So here you have like a thin rod about the center, so it's symmetric and spinning maybe like an airplane propeller. So that's actually going to be 1/12 ml squared. Then we also have maybe the same, thin rod, so like an airplane propeller, but maybe we're just looking at one of them from the center of the propeller instead of like, maybe two as in the first picture. So here we have a thin rod spinning about the end. You'll notice that this is actually 1/3 ml squared instead of 1/12 ml squared. We also have like a plane spinning through the center or spinning about its edge. We have cylinders, a circular hoop, spheres, depending on how they're rotating. So what you'll notice is that it's always some sort of like coefficient, some value, the mass of the object, and then here it could be like the length of the object, it could be the area of the object, or it could be maybe the radius of the object. So all of these are squared. So there is a pattern to it, a way you can calculate it. And it just depends really on the object that you're looking at of exactly how it's calculated. Uh-oh. Oh, I see. There we go. Okay. So let's talk about actually putting all this together. So we have K being rotational energy and how that's going to relate into the mechanical energy. So if there are no dissipative or external forces, then an object's mechanical energy is conserved. Okay, we've talked about that before in the last set of lectures. No dissipative forces, your delta E, your E mech is going to be the same. So for this case, delta E mech, the change is 0. Now, what's interesting here that you'll notice is we have, okay, here's our mechanical energy, but then we also have this, okay, our mechanical energy equals rotational energy, but then I also included gravitational potential energy. You can even see that here. So here's our energy from rotation, 1/2 I omega squared. We literally just built that. And then we're going to add on the gravitational potential energy, mgy. And the reason that is if the axis of rotation is not through the center of mass, then the rotation may cause the center of mass to move up or down. So since the center of mass actually may move up and down, that's where we're actually going to get or lose some gravitational potential energy. So in this case, the object's GPE will change. And you can see that here. So if we have this bar that's sitting here at the origin, right? So GPE equals 0 here. It's setting in line with the origin, so there's 0 gravitational potential energy. But then if it swings, because it is on a hinge, we can see that here. Since it is on a hinge, that mass is going to move below the origin, right? So not only does it have rotational energy, K rot, but we're also going to have a change in potential energy. So those need to be accounted for off-axis rotations. And that's why when I talk about the mechanical energy of this rotational situation, the gravitational potential energy is also included. So let's actually do some math with this example. So if we have this 1 meter long, 200-gram rod that's hinged on one end, and it's hinged on one end connected to the wall. If it's held out horizontally then released, well, what is the speed of the rod when it actually flies down and hits the wall? So this rotation is not about the center of mass. So the gravitational potential energy does change, right? That center of mass is actually dropping below the x-axis. We have a negative y value. But there's no dissipated forces, so we do know that the total potential, or the total energy of the system, mechanical energy, doesn't change. Okay, well, we need to use the parallel axis theorem since the rotation is not through the center of mass. But before we actually calculate that I value, let's look at what we do know. So we know we have some initial stuff, initial kinetic energy and potential energy, and we have some final kinetic and potential energy. Come on. Oh, this is so buggy. There we go. Okay. Well, we know that the final rotational energy, that's, let's back up. So we know the initial kinetic energy is released from rest. Okay, so the initial kinetic energy is 0. And we know that since it's sitting in line with the origin, it has no initial gravitational potential energy. Okay, so that's actually going to cause all of our initial stuff here to be 0. Now, if that's 0, that means just the final rotational kinetic energy and final gravitational potential energy, they also have to equal 0. Okay, so we can actually plug these in. We know what the formula is for the rotational kinetic energy. We know what the formula is for gravitational potential energy. They equal 0. Well, we want to know how fast it hits the wall, so we need to solve for omega final. Okay, so from our original equation here, that's just an algebra problem to actually solve for omega final. One word of caution here, you'll notice that there is a negative sign, okay? So anytime you see a negative sign under a square root, be careful because you can't take the square root of a negative number without getting an imaginary number. So be aware. So what's going to happen is we know that our y value, when this thing swings, the center of mass is going to go negative. So a negative times a negative is a positive. So anytime you see a negative under your square root, make sure it's going to work out to where the number in there is actually going to be positive. All right, so now we have solved for omega, but we still don't know what I is. See, we have the answer to what we want to know, omega f, right? We have the answer, we just have it symbolically, so we need to plug in some things. Okay, well, we know that the linear mass density is uniform. So the dm dx really is just the total mass of the whole thing divided by the length of the whole thing. That's what you get if it's a uniform object. We don't have any weird changes, so we can just do the whole mass divided by the whole length, done. Okay, so that's our linear mass density. Okay, now let's first calculate the center of mass, because we need to know that first, right? We need to know the moment of inertia about the center of mass, and then we can shift it with the parallel axis theorem. Okay, so we'll just do this simple calculation. Notice here, I'm going to rewrite dn. Now, I do that just by getting it from our linear mass density. So dm is just going to be lambda dx, but we know that's just the total mass divided by the length dx, okay? That just comes from rearranging these differentials, just like the fractions. So we can change the dm to something useful. Okay, so I do that. It looks like I can pull my constants out front, this m over l, they're constant, they're not changing. And then I just do a simple integral of x squared. Okay, so that's going to give me 1/3 x cubed. And then I'm going to Solve for my limits, no weird u subs or anything, and I get 1/12 ml squared. And that's actually correct. We can go back to that table that I supplied on a previous slide, and you'll see that 1/2 ml is actually the moment of inertia for a rod on the end, like an off-axis end point. Sorry, no, that's for a rod around the center of mass. Now we need to take that and shift it so that it is a rod around the endpoint. So the 1/12 ml squared actually does check out as per our table. Now we just have to simply add the little shift on here, and that's just going to tell us how we take this moment of inertia and then shift our point of rotation over to, right, so from the center of mass, we want to shift it over here to this new axle or point of rotation. Okay. Well, the distance to the center of mass is just half the length because the center of mass is in the middle. So we're going to plug in let's see, here we go. We're going to plug that in. Crap. I have made a mess. Let me clean this up real quick. So we're going to take the L over 2, and we're going to plug it in right here. So that's going to be L squared over 4, essentially, because it is D squared. So here's our M, our D squared, and then we simplify. We add it to the center mass part, and we get 1/3 ml squared. Okay, so that's just the moment of inertia. So finally, we put all this together. Okay, we're going to plug in that moment of inertia we just found, and we're going to simplify the crap out of this. Okay, so we also know that our center of mass is at L over 2 here. Oh, sorry. So the y coordinate of the center of mass final. So after it's fallen, we can go back here. You can see that the y coordinate here is negative L over 2 because the center of mass is at the middle of the rod. And when it falls down, the middle of the rod is going to be at negative L over 2. Okay, so there's our center of mass. And all of this actually simplifies quite nicely. So this is our omega, right? And if you take a moment and look at the units, you'll find that they work out quite well. So this is our angular velocity. But we want to know what the tip speed is of this thing as the rod falls from here to here. What's that final tangential velocity? So we can take this angular velocity that we found, right? And all we have to do is just multiply by r, and that's going to give us that tangential velocity. So r in this case is just L because that's the tip. It's the whole length of the rod. And that's going to simplify to just square root 3gl. And it turns out that's going to be a final tip velocity of about 5.4 meters per second. So just a quick summary. Sorry, I went over by a little bit. My apologies. So an object naturally wants to rotate about its center of mass. Okay. The center of mass is a mass-weighted center of the object, so you can calculate it with some basic weighted average functions. If it's a nice continuous object, you can even turn those into intervals. So rotational energy is actually given by 1/2 I omega squared. That's how we calculate just the rotational component of this energy. I is the moment of inertia, which is the rotational equivalent of mass. Okay, and we can actually calculate that with this integral here. Just the integral r squared dm. The parallel axis theorem, which we talked about, you can actually use that to shift the moment of inertia for any sort of off-axis rotation. Okay, and that's just whatever the typical standard moment of inertia would be for an object, you would just add this extension for an offset axis md squared. And then for rotational motion, if it's off axis, it's just going to be the rotational energy of the object, or the total mechanical energy is going to be the rotational energy of the object plus any changes that the center of mass undergoes during this rotation. So if it's an offset wobbly wheel, and it's spinning vertically, you know, that object's going to like jump up and jump down while it's rotating. So you'll want to include that gravitational potential energy as well. All right, so this was the first introduction to rotational energy. Hopefully this will be the longest lecture of this series. There'll be 2 more. Hopefully they'll be a little shorter. But I did want to include several examples in here. So as always, if you have any questions, please let me know. And otherwise, I hope you look forward to the rest of these rotational dynamics lectures.